Thank you very much, Benoit, for that introduction. So in this seminar, I'm going to go into a little more detail regarding some of the topics that were mentioned in seminar 2. To start with, I'll talk about the key challenges of using silicon as an anode in lithium-ion batteries, mainly silicon expansion and degradation. And secondly, I'll talk about the evolution from the first to third generation types of silicon anodes, and I'll explain what I mean by each of those generations and the different strategies that are being used to overcome the limitations. And finally, there'll be some takeaway and conclusions. So the first section, key challenges, silicon expansion and degradation. And I think, so before I go into the details, I want to just take one step back to talk about what is the ideal anode for a lithium-ion battery and the main properties that it needs to have. So first of all, it should have high gravimetric and volumetric capacity. It should have a low potential against the cathode material. It should be able to display long cycle life, or at least a cycle life commensurate for the application. It should be lightweight, which is of course linked to the high gravimetric and volumetric capacity. And it needs to be environmentally sound, low toxicity, and low cost. So basically also widely available, making a low cost method of production. Now, to start with, I'll compare silicon to graphite. So graphite is currently the anode of choice in lithium-ion batteries. And in in graphite anodes, the lithium intercalates between the graphene layers of the graphite with a ratio of about 1 lithium to 6 carbons. In silicon, we know that's different. The silicon alloys with the lithium, forming a metastable alloy of lithium-15, silicon-4. So in principle, that's almost 4 lithiums for every silicon in the material. And that gives us a much larger theoretical capacity with silicon, which is what makes it so attractive. So for graphite, you have a capacity of 372 milliampere hours per gram. With silicon, that can be almost 10 times as much. That comes at a certain cost, however. So in the case of graphite, the lithium is constrained within the atomic framework. You actually get an expansion of full capacity, a full lithiation of around 10 to 13%. Whereas with silicon, as mentioned, the volume changes are much larger, up to 300%. This means the graphite is stable on cycling, whereas in the case of silicon, there are large volumetric and structural changes on cycling, which need to be dealt with in some way. So I'll just give a little recap of what was mentioned in the previous presentation, previous seminar about the electrochemistry of silicon. Now at 450 degrees, if you lithiate silicon, you'll go through a series of different, I've shown in the right-hand side here. You go through a series of different lithium silicon alloys, eventually ending up with lithium-22 silicon 5, which corresponds to 4,200 milliamperes per gram. And this is the material that has a theoretical expansion of 311%, as taking us back to the question earlier. In the case of room temperature application, so in a real lithium-ion battery, you will actually go through a crystalline to amorphous phase transition during the first lithiation, because the formation of the different alloys are kinetically hindered. You'll get a single phase transition seen here at 0.1 volts, leading to the metastable lithium-15 silicon 4 phase at less than 50 millivolts. As you see in the bottom picture here, what happens is you go from crystalline lithium silicon to lithiated to this crystalline, metastable crystalline lithium-15 silicon 4 in the first lithiation, and then you will cycle between that and amorphous silicon in all subsequent cycles. As mentioned, silicon expands a lot on lithiation, and this leads to several mechanisms for silicon degradation. The first is material pulverization. This is where the lithiation causes stress on the structure, leads to cracking of individual particles and a lack of electrical contact. This can also be extended in the second mechanism to overall electrode expansion, where particles expand and impinge on each other during lithiation. During delithiation, they will then contract, and this can lead to detachment from the copper collector and challenges for the overall full cell design. Third mechanism, degradation, relates to the solid electrolyte interface. Now, the solid electrolyte interface is a layer that's formed on the anode surface from the reduction of the electrolyte during the first lithiation. A stable solid electrolyte interface is crucial to having long-term cyclability, and it should be dense and stable. It should be ionically conducting and electrically insulating. What happens with silicon expansion and contraction is that this SEI will break, leaving new silicon free for further reaction, leading to further electrolyte decomposition, creating a thicker SEI. This leads to longer lithium diffusion through that SEI and also increases the mechanical stress on the system. So these are the three main mechanisms mentioned in the first section. So those are the key challenges we face. I'll now introduce the three generations of silicon anodes and the strategies that are being used to overcome the limitations. So as mentioned, there are three different general options, classes of silicon usage in anodes for lithium-ion batteries. The first generation is the use of silicon or silicon oxide as an additive at less than 10 weight%, often as low as 1 to 3 weight%. This is a powder additive, and this has already been on the market for several years. I'll talk a little bit more about that in the next slide. The second generation, silicon carbon composites. These are 30 to 50 weight% silicon contained within a rigid carbon shell, and these have arrived on the market in 2025. The third generation, silicon dominant anodes. So these are usually greater than 80 weight% of silicon, where there's silicon providing the full capacity, and either they can go up to 100% silicon, but sometimes carbon is added in small amounts to provide electrical conductivity. And these are expected on the market, say 27, 28. The first set of first option, the first generation, silicon additives. As I mentioned, these are less than 10 weight% of silicon, and these were basically the low-hanging fruit in the development. The side effects are minimized by only having a small amount of silicon present, but then, so of course, is the gain achieved from that, with the balance being graphite, of course. These were first demonstrated in 1994. They are usually prepared by thermal evaporation of silicon or silicon oxide, followed by rapid quenching. And the advantage of these, they don't require any major process changes, so they're essentially a drop-in into the usual production battery manufacturing process used with graphite. And these, as mentioned, have been present in commercial products for several years. The second generation are silicon carbon composites. Now, I've shown a schematic on the right-hand side here. The actual structures being used in commercial products are a little bit more complex than this, but what you have essentially is a carbon shell surrounding a void space containing silicon particles. During the first lithiation, these particles expand freely within that space, but without breaking the carbon shell. And the carbon shell also obtains a stabilized SCI on its surface. In the subsequent cycles, you then go through delithiation and lithiation within that structure. Now, The advantage of the stabilization of the SEI on the carbon surface is that these are compatible with standard electrolytes used with graphite. They can display long cycle life, capacity retention, and have high Coulombic efficiency. Some of the cons of these systems are that the deposition of silicon is usually by a silane route, and therefore upscaling requires proximity to a silane plant. The third generation of silicon anodes, as I mentioned, are the silicon dominant systems. I'll talk about three different possibilities for that. The first is silicon nanoparticles. Silicon nanoparticles can undergo large volume strains without mechanical failure, which solves the first issue mentioned of the three problems that we are facing. However, it does not fully solve the issue of large volume expansion. So you still have a large amount of swelling, and that can make it difficult to maintain electrical connection. There have been attempts made to solve this using flexible polymer binders combined with conductive carbon additives, or using conductive polymer binders. On the other hand, the cons of these systems are that nanoparticles are more expensive to produce than micron-sized silicon, and they're also more difficult than micron-sized silicon to process into electrodes. Second option here, second development, is silicon nanowires. What I've got shown here is an early development of silicon nanowires. The actual ones that are being developed for commercial applications have more complex structures now. But essentially, silicon nanowires work by being grown directly onto current collectors. So for example, a copper current collector, with one end bonded to the metal substrate. And what you have is good electrical contact and a 1D electronic pathway vertically along the nanowire, and you have space to expand in between the nanowires, so the nanowires can relax horizontally here. The original versions, as I mentioned, had a crystalline silicon core, and that meant that you can maintain this stable electronic pathway along the core, and an amorphous silicon shell, as long as the potential was maintained at about 120 millivolts versus lithium plus. These are usually made by CVD deposition these days, and again, manufacturing at a large scale needs to be coupled with a silane production facility. Third option I want to talk about are micron-sized particles, and this is the area in which E-magy are busy. So E-magy produce micron-sized nanoporous silicon particles intended to be used for silicon dominant anodes at greater than 85 weight%. And what you see here in the picture to the right, and then underneath in the schematic, you maintain within this particle a stable crystalline silicon backbone, and during first lithiation you form lithium silicon and the amorphous alloy within the pores, the amorphous structure leading to the crystalline metastable alloy. But if you stay below 2000 milliampere per gram capacity, you can retain that crystalline backbone and allow, therefore, for the swelling and expansion internally within the structure. So, as you can see in the bottom schematic, that in subsequent delithiations and lithiations, you basically empty and fill up the pores. Now, of course, I should say that you're also coating the structure as well, but for the purpose of the schematic, that's not shown here. That solves two of the issues in terms of the expansion, but there's still the SEI question, and alternative electrolytes are being developed in order to solve this SEI question, which affects silicon anodes broadly. So I've just included a couple of slides here to just introduce the concept of novel electrolytes for use with silicon. Now you can see here in the right-hand side, in standard electrolytes, lithium salts are completely dissociated, leading to lithium having its own solvation sheath. So you can see here in part D of the figure on the right. What that means is during lithiation, you have solvent decomposition, and that means you get an organic rich SEI layer on the silicon surface, which is not stable upon cycling. What you want is to not have the lithium salts fully dissociated and to form an inorganic SEI layer, an inorganic rich SEI on the surface, which will be more stable. And that is not possible with the standard electrolytes currently in use. So just to mention a few options of how you can get around that. The first thing you can do is to increase the concentration of the electrolyte. I won't go into the specific chemistries here. I'll just highlight the different concepts. So firstly, you can have a highly concentrated electrolyte in order to reduce the degree of dissociation. But this comes with a downside, and generally that's that the electrolytes become more viscous, you have some transport issues, and generally they can only be operated at lower C rates. So there are a couple of other options being investigated to try and solve this third problem. The first is the use of locally highly concentrated electrolytes. And here you use a diluent to dilute, which doesn't interact with your lithium salts. And therefore it acts a bit like a highly concentrated electrolyte, but with local high concentration. The second option are weakly solvating electrolytes. So they have a low dissociating power versus the lithium salts, and that leads to the same overall effect. So that was my last slide. Just a few conclusions and takeaways. Firstly, silicon fulfills many of the criteria for an ideal lithium-ion battery anode. Secondly, efforts are being made to overcome the mechanisms of degradation caused by the silicon swelling. Now, silicon is already on the market as an additive in graphite anodes and has reached the market in silicon carbon composites. And finally, novel silicon-dominant anodes are coming, and the challenges are being overcome through methods of nanostructuring and also through the use of novel electrolytes.